All right. Here we go. All right. It says calculate your chi-squared value. This is on page 127 for an observed. Hey, what's happening? We're on page 127. Calculate your chi-squared value for an observed value of 4.2 and an expected value of 3.8. Show your calculation. All right. We ready? Here we go. All right. So remember, in order to find the chi-squared, it's going to be observed minus expected quantity squared over the expected, right? So it says calculate your chi-squared value. So we're going to do observed of 4.2 minus 3.8. We're going to square that. And then it's going to be divided by that. So if we just do the math, let's see. 4.2 minus 3.8. Square that. Oops, clear. You can do this, Stirrup. 4.2 minus 3.8 squared divided by 3.8. All right. So this cut has a chi-squared value of 0.04. Okay, observed minus expected quantity squared divided by the expected. What does it mean when chi-squared is equal to 0? This means that our observed and our expected are the same. Does that make sense? All right. Hey, page 127 when you get it out. All right. So Ben and Jerry's, Ben and Jerry's ice cream. This is good stuff. All right, so moving up to the thing, Ben and Jerry's sales distribution. They have some data here that they shared with us. I like Ben and Jerry's ice cream. I'll take that. All right, so looks like Half Baked, 15% of their sales. Cherry Garcia. I like Cherry Garcia. It's 12%. Chocolate Fudge Brownie is 10%. Cookie Dough is 8%. Fish Food is 7%. And Other is 48%. All right. Ryan, there's yours. There's yours. All right. Here we go. Here we got to try. All right. Hey, something interesting. See who's paying attention. Can I get a chi-squared value that's negative? No. So a chi-squared value, because it is observed minus expected quantity squared over the expected, this is always going to be positive. Okay? Which would be interesting when we start doing the chi-squared distribution, which I know that's why you came to school today. Chi-squared distribution looks like a normal distribution, deals with degrees of freedom, but it doesn't, the chi-squared tail doesn't go into the negative x values. I know you can't wait to see that. It's exciting. All right. So let's see. We have Half Baked. We have Cherry Garcia. We have Chocolate Fudge Brownie. We got Cookie Dough. We got Fish Food. Yes. And then we have Other. All right. So the first thing we need to know is this came out to 15% for this one, 12% here, 10%, 8%, 7%, and 48%. All right. So it says we did a random sample of 286. So this is our expected, but we need to convert the expected to an actual number. So we're going to multiply each of these by 286. Okay, and random samples we like. So 286 times 0.15, that gives me 42.9. And then 286 times 0.12, it gives me 34.3. And 286, that's going to give me 28.6. And then 286 times 0.08, that's going to give me 22.9, rounding to one digit. 286 times 0.07, and that's going to give me 20.0. And then 286 times 0.48, 137.3. All right. So those values, those are our expected values converted from the percents into what we'd expect if we had these 286 sales. But things that we found, we observed from our sample that there was 32 here, 35 here, 28, 16. Oh, that's 26, sorry. 26, 16, and 149. All right, so I got to move our chi-squared. I'm going to move this up here out of the way. All right, so then we need to make our last column, and we're going to use that above equation. Yeah. Yeah, let's make our null and our alternative. So 3, our null and our alternative. So ice cream equals, we'll go our expected. Ice cream not equal in our expected. Make it simple. Okay, there's 3. So this one, I guess, is technically number 4. All right. So using the above equation, I'm just going to run through it, see what we do. So 42.9. Oops, clear. 42.9 minus 32, quantity squared, divided by 32, divided by expected. Sorry about that. 42.9. Biscuits and gravy. I made a mistake. 42.9. Thumb got in the way. Minus 32, quantity squared, divided by 42.9. There we go. So that comes out to 2.8. 34.3 minus 35. So 0.7 squared divided by 34.3. So that comes out to 0.01. And then 0.6 squared divided by 28.6. Wait, so that's one I already did. I think this one is 0.01. Hang on, I might have made a mistake on the above one. So 34.3 minus 35. Square that. Divided by 34.3. Oh, came out the same. Those were both the same, I thought. 22.9 minus 26. 3.1 squared. Divided by 22.9. So this one comes out to 0.42. 4 squared, 16. Divided by 20. This comes out to 0.8. And then the last one, 137.3 minus 149. 11.7 squared divided by 137.3. 99. All right. So that's how you would do number 4. So using the above equation, the observed minus expected quantity squared divided by the expected is how you get chi-squared. Notice all those chi-squared values are indeed positive. The reason they're positive is, first off, we're not going to get expected negative values. And then also because I'm squaring a quantity. Yeah, so that'll take place. All right. So that is problems 3 and 4. Questions about that? Now, at a point soon, we're going to have to, probably on the next page, we're going to have to add up 2.8 plus 0.01 plus 0.01 plus 0.02 plus 0.8 plus 0.99. And that's actually what we saw. All right, Stirrup's favorite thing to talk about. Dice. Oh, oranges first favorite, yeah. Dice second favorite.
All right, I mean the bones.
The bones. Throwing the bones.
Yeah, throwing the bones.
All right. It says a die manufacturer tests to see if the dice they make show an equal distribution of 1s, 2s, 3s, 4s, 5s, and 6s. They roll a single die 1,000 times to test if this is correct. Okay. So you hope that each side of the die has the equal chance of showing up each side, right? All right, so for number 5, we could say that our null and our alternative. So we can do this, clear. So each side of die is equal to a 1 in 6 chance. Each side of die not equal to a 1 in 6 chance. That's kind of simple, isn't it? Why is it 1 in 6? Well, there's 6 sides. What if it lands on the edge? We don't count it. All right, and then create a table. Cool. All right, so let's create our table below. So die 1, 2, 3, 4, 5, 6. What we expect is 1 in 6. So what we could do is we're doing 1,000 times. 1,000 divided by 6. So we are expecting 166.67 Now you're going to ask, how did I roll a 0.67 of a die roll? Well, I guess you didn't, but so this is the expected. And then they find out that we observed 158 of these, 170 of these, 164 of these. So those are going with each other. 154, 178, and 176. Cool. And again, we're going to use our equation, which our chi-squared is equal to the observed minus the expected quantity squared divided by the expected. Bless you. So our chi-squared value. So 166.67 minus 158. Square that. Divide that by 166.67. So this came out to 0.45. And 166.67 minus 170. Dang it. 170 minus. Square that. Divide that by 166.67. So this is fascinating. This is 0.07. Square that. Divided by 166.67. That comes out to 0.04. Let's see. Square that. Divided by 0.96. Almost done. 166.67 minus 178. Square that. Divided by 166.67. That comes out to 0.77. And 166.67 minus 176. Square that. Divide that by 166.67. 0.52. All right. So that is all of the information based on this 5 and 6 so far. So do you guys feel comfortable with how that's being done? It's not really the hardest math, but I think you could get confused a little bit. All right. Which outcome produced the largest chi-squared value? In context explained. Which has the biggest chi-squared value? Well, it looks like the 1. No. It looks like the 4 came out to 0.96. So this 4 is not as likely to have happened. It could have happened by chance. I'm sure it did happen by chance. But that's what it means in context for 7. Then it says find the total value of all the chi-squared values. The moment you've all been waiting for when we add up all the chi-squared values. So here, I put number 7 up. So number 7 is rolling a 4. Least likely. Could be just that it was a chance that happened. Okay, so now we have to add up all our stuff. So I have 0.45 plus 0.07 plus 0.04 plus 0.96 plus 0.77 plus 0.52. So add all up, which equals 2.81 is my sum of chi-squared. Okay? And then which outcome was the least likely to occur if the null is true? Okay, so this is the answer for number 8. So which is likely? Which one's least likely? The 4 is the least likely. It's the largest chi-squared. Do I?
If the null is true, doesn't that mean that they all have an equal distribution? So it'd be all.
Oh, hang on. Maybe I answered this wrong. Which outcome was least likely to occur? So the null is true, so we're expecting that you have a 1 in 6 chance. So you have to have the highest chi-squared value, so it has to be the 4. The 4 is the most likely not to have occurred. Thanks for checking. What time we at here? Oh, sweet. I do have time. All right. Put your names on it and hand it in. Maybe I'll just start. I do like this. Homework. All right, so flip your books to 7-3, page 51, please. assignments, we created tables which observe the expected chi-squared values were computed. The sum of all the chi-squared values is the measure of the total of deviation from the null hypothesis expected. Okay? The larger the sum of the chi-squared values are, the stronger the evidence is against the null. Okay? So if you sum up your chi-squared values, the larger that number becomes the less likely your null hypothesis is true. However, chi-squared values do not follow normal distribution or t-distribution. Guess what, guys? We got a new distribution. It's called the chi-squared distribution. Aren't you excited? This is why you got up today. Like the t-distribution, the chi-squared distribution changes the shape somewhat depending upon the degrees of freedom. Several chi-squared curves are shown below. So chi-squared degrees of freedom 5 looks like it's totally, any of your chi-squared values are all going to, unless you have like, degrees of freedom like 1,000,000, they're going to look like they are all skew right, meaning it's being pulled to the right. Again, chi-squared values, you don't have less than 0. Okay, so it starts at 0. You don't deal with any negative numbers. Chi-squared distribution skew right. We said that. So less degrees of freedom increases, makes it more and more skew. Okay. So calculate. We have that. We're good. All right. So flip the page, and we can do the chi-squared distribution. You with me? All right. All right. Hey, we've done the baseball card one over and over. So remember, we went out and selected 40 boxes of this cereal, hoping to get all 5 of these cards. We are expecting that if we selected 40 boxes, that we would get 8 of each card, being A, B, C, D, or E. We actually didn't get that, so we created a chi-squared value. We went, observed minus expected quantity squared, divided by the expected, and that's where these values came up. Okay, so the total chi-square of this is exactly 2. Okay, so our chi-squared test statistic is going to be 2. We're going to use a chi-squared with 4 degrees of freedom. Now, this is where things you might goof up. I have 5 categories. Agree? Degrees of freedom is 1 less than that, so that means our degrees of freedom is 4. Okay? So, if we jump onto our favorite website, Desmos, here we come. All right, so on this particular one, we have 5 cards, so our degrees of freedom is going to be 4, which is fine. Come on, Desmos, here we come. Best day ever. All right, so a few things to know. You go down here to functions. We want to figure out where the chi-squared is. So go down to your distributions. So we've dealt with normal. We've dealt with t. Now we're going to do the chi-squared distribution. Okay. So chi-squared distribution. Oops. Get rid of that. Chi-squared distribution. And then notice it says enter degrees of freedom. There's 5 categories. Degrees of freedom is 1 less than that. So my chi-squared of this, degrees of freedom 4. This is what our distribution looks like. So notice, yeah, it has a hump, but it's definitely skew right. Agree? Remember that term from first semester? All right. So if I wanted to see, it says we are going to figure out if this meant anything. So we're gonna look for our p-value in this case. So I'm gonna go from 2 to infinity. Okay, 2 to infinity. We're coming up with roughly 0.736. Looks like the book has 0.735. We're better than the book. It says, recall, if the p is less than alpha, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. In this case, a reasonable alpha value might be 0.05. Okay, so we're still testing at 0.05. So we fail to reject the null. If the p-value is larger than 0.05, we fail to reject the null. We do not find strong evidence of this data had any difference. Okay, so 0.736 is larger than 0.05. Agree? That means that we are going to fail to reject the null. We did not find evidence against the null. Our selection of these 40 boxes of cereal, having our 11, 7, 6, 9, and 7 of cards A, B, C, D, E, was just mere chance that it happened to be that way. It doesn't mean if we keep selecting that it'll continue to happen. Okay? So there are really two assumptions or potential red flags to watch for. Sample size must be large enough. In a chi-square test, this is met when all of the expected values are greater than 5. Okay, we'll come back to that. And random sampling, we must assume each box is randomly chosen from a sample. So it says, chi-square test is the expected values are greater than 5. Okay? So, expected values, all of these are 8. Did we satisfy it? Yes. This is bigger than 5. Okay? But if you recall, when we did this problem originally, it just said we went to a grocery store, took 40 boxes of cereal. We didn't have randomness. So, might be a red flag that we didn't have the random situation take place. You guys all good? Social media telling you what you need? Yes, sure. Great. All right. So for tomorrow, page 129, take a look at it, work it all out completely, finish it before you come to class tomorrow. Yeah, right. So that's all I got. So sweet, I was able